have Chen, Dr. Chen, who is joining us from Google AI, which is literally just a mile and a half from here in the center of Gunita. So he hasn't had to travel a very great deal. Chen tells me that he did his PhD with Alan Goldman at the University of Minnesota. Then he was in John Martinez's quantum computing group here at UCSB before transitioning about 8 years ago to Google AI. And he's going to tell us this afternoon about beyond classical quantum computing. And we're really happy to have you here. The scheme is that we would like you to spend 40 minutes on your talk, and we're going to use 20 minutes up for interruptions and questions. We're a rowdy lot, so please forgive us. Like Russian physicists, you know what they're like. Okay, thank you.
Thank you. Good afternoon, everyone. My name is Yu. I'm a research scientist in Google. It's really a pleasure to be back, and thank you for the invitation. As Peter already said, a couple of years ago, I was literally working next door in Florida with all the measurement and fabrication.
Are we on Zoom?
Good question.
Because it's not picking up the voice.
Okay, it does have QNSI Zoom in the top right corner, but maybe you need to unmute.
On Zoom?
I don't think we
there is a button. Yeah, there is something you have to do on the screen here, no, not on that. Okay, that is active. Yes. Good.
I will check.
Good. Everything goes well. Let me come back. Okay, so it's great. A pleasure to be back. So today, I will talk about some progress I've been making towards beyond classical quantum computing here in Google. So, of course, the best way to start the talk is always thank you for the fantastic team. We have a team all over the world at different locations, mostly between Europe as well as US. It's a team of about 200 people as of now, and it contains research scientists, engineers, scholars, and intern students. It's really an honor to work with such a fantastic team. Cool. So what are we doing in Google? So this is not the first time we actually show this in public. A couple of years ago, we really released this to the public. Our goal, ultimate goal, is to build an adequate computer, and then really Google is committed to this. This is a very big goal because this will take us a very long time to build such a giant system. That is why instead of just only focus on this goal, we break that into a set of technical milestones. Those technical milestones are naturally associated with the size of the system, will continue to grow. And more importantly, they're associated with those technical achievements. We're good? Okay, thank you. Then we are very happy out of those set of milestones. We have already achieved two. In 2019, we published a paper in Nature, talk about the first beyond classical demonstration, which we will cover briefly today. And then earlier this year, we really spent a good amount of time focused on error correction, and we showed the first logic qubit prototype. Now, what's more importantly, going forward, there's a lot of challenges. There's still 4 more big milestones ahead of us, and exponential increasing as in terms of complexity. And before we actually eventually can reach this final goal to build error correction quantum computer. I would say, of course, this is not the goal for only of us. In fact, this is, I would say, it's a global technology race. It's a race between different teams, between different countries, and more importantly, I say, between different technical platforms. Even here in UCSB, I know there's a lot of wonderful researchers that are doing fantastic progress on atom, spin, ion optics. Specifically, here in our group, Google, we focus on so-called superconducting circuits. So let me give you just a 1 minute one-on-one. What this is. In fact, it's rather simple. So superconducting qubit is basically mostly focused on superconducting qubits. It's nothing but a nonlinear oscillator. So if I have you focus on the plot here, everybody knows oscillator is simple. Well, oscillator is basically formed by capacitor, shunted by inductor. It's simple like that. Once you have that, you're good. For superconducting qubit, it's the same phenomenon. There's nothing fancy. I have a capacitor, which is the center pad here, together with ground. And I have this special thing at the end. It's an inductor, but in reality, it's something we call Josephson junction. Many of you are familiar with this. Josephson junction is nothing but a sandwich structure with two superconductors sandwiched by a very thin layer of insulators. The special thing of this, once you have a Josephson junction, what you can do is you can take this as a nonlinear oscillator, nonlinear inductor. So what that means is if you look at the qubit potential, With the linear oscillators, inductor and capacitor, you have a problem. However, if you have a Josephson junction, the potential now becomes sinusoidal. So with this little bit nonlinearity, this becomes very good because now you have quantized energy levels, and those energy levels are not even anymore. You have nonlinearity. So you can individually address those, but the core of this is simple. It's nothing but a nonlinear oscillator. It's simple. Good. But there's a lot of advantage associated with kind of way to build quantum computers. As I told you repeatedly, this is a capacitor, inductor, and nothing else. So for those of you work or study about the integrated circuit, you can just copy paste this everywhere, and this is the integrated circuit. We have, human beings probably have over 100 years of experience working on a circuit like this. So you know how to design this, you know how to optimize this. It's easy to integrate and scale up. And if you design carefully, you can choose the frequency you want to control on the range of just several gigahertz. So this is something you can literally buy the electronics off the shelf to control this. So this is rather simple and straightforward. And finally, after many years of hard work, especially on material, which is the thing I'm looking forward for the panel discussion, is right now we're really talking about you can do many, many gates during the lifetime of qubit. We're already approaching something, we're already doing something like 1,000 gate, and we're already starting approaching something like 10,000 gate within the lifetime of qubit. So it's a very good progress in this direction. However, it doesn't mean we don't have challenges. We do have a lot of challenges. I'm not going to have time to cover all the challenge in detail, but only thing I want to tell you is the technical developer wanted to develop, go from nanoscale, where we're pretty much focused on material. We really care about defect, we really care about coherence of qubit, we really care about the interface between the different materials. This is something like core to our heart. On the other hand, go from nanometer all the way to meter. We build those large bridges. We really care about how to build large cryogenic systems that can house many, many hardware inside this system.
So
and between those two,
can I just ask, what is your definition of coherence?
coherence goes to two ways. Coherence is those, think about if I give my qubit some energy, how long it decays. So that we call dissipation. So T1. And then there's a different coherence, which is related to phase. When you have qubit, you have energy level, you also have phase associated with this. How long that phase got lost, we call T2 or T2 star. It varies from platform to platform. For the specific qubit we're working on right now, we're talking about hundreds of microseconds, approaching to millisecond lifetime.
Is it based on like quasi-particle lifetime, or is it a different idea?
That's a very good question. What's limiting our coherence? Coherence is a budget. So instead of writing T1, which is time, you should write 1 over T1, which is a rate. Then you add a lot of rate up. Quasi-particle is one of them. Intrinsic dielectric is also one of them. Vortex, there's many, many challenges. Even the design itself, I can have resistor next to it. You never know. So it's, in terms of coherence, it's probably one of the most complex challenges we're dealing with.
So it's a combination of other effects, not just the lifetime.
Exactly. It's a budget.
Okay.
Yes, exactly. All right. So as I said, coherence is a big thing for us, but between those two, let's go over 9 orders of magnitude. We care about a lot of fabrication, packaging, electronics. We do a lot of things in-house. We just have to build everything. I do want to highlight one single thing, though, is chip design and fabrication. And I want to show you some of the examples. For example, we are using flip chip architectures. In other words, if you look at this example, I have the qubit chip, which I'm showing here with a line of qubit. In this case, I think it's 6 of them. And now I have another chip, which is a carrier, where we start about the wires. And then what you have to do is take this and flip it up, and then bond them together. That's how you do control. You separate the coherent part versus non-coherent part. In addition, we build rather complex structures, like we do L-bridge and crossovers to connect wires. We do tunnel wiring. We do a lot of this. One of the here, because a lot of structures we have developed is happening here in-house in USB Clean. We very much appreciate the partnership with USB because that really takes us a lot of knowledge. Good. So with that brief highlight, please.
Can you tell us a tiny bit about your superconducting substrate? What do you use for that?
We use a combination. We start with sapphire, and then it's very good. It's super clean and easy to process. However, you have a challenge if you want to do a little bit of scaling up, especially for 3D integration focus. So more recently, we switched to silicon, which is more conventional because a lot of compatibility for fabrications.
And your superconductor for your junctions?
The simplest one, that is aluminum.
Aluminum.
That doesn't mean other superconductors should not be considered. And more recently, in the last couple of years, I mean, there's new material like tantalum. People look at most clean interfaces, especially between metal and air. We think this is much more clean compared to aluminum, and see big jumps in terms of coherency. So alternative material is actually a big research field in superconductors.
Thank you.
So is the main consideration then how clean it is, the superconductor?
How clean?
I mean, no, I mean, is that the main consideration of the choice of the superconductor is how clean it is, or?
It's a little bit complicated question because the way we think about it, we have, on paper, we have LC, right? We have inductor capacitance. How clean it matters depends on where the electric field is distributed. In an area that electric field concentration is high, which is mostly the junction area, the cleanness of the material is super critical because we see defect. Those defects we suspect is coming from just something sitting in the junction with a little bit of atomic defect. You can create those things. This is important because that creates a big, because your T1 can be on 100 microsecond, but if you have a defect, it goes to like a microsecond. You literally that at that particular frequency. On the other hand, the cleanness of the bulk material, I show you a big capacitor pack. It's unclear whether or not that's supercritical. You can argue about that, whether or not that falls back to the general material loss, but you don't see those big defects anymore. It really depends on distribution of electric field.
When you say cleanliness, do you mean like is that the same as disorder in the material?
Can you repeat the question, sir?
Is when you say clean, does that mean like a material with low disorder, or
Yes.
is that not exactly the same term?
Yeah, next, superconductor, as many of you know, has this property. It's less sensitive in terms of superconductivity itself to defect. You're completely okay. On the other hand, when you're close to a regime at high electric field, the structure defect especially is something we particularly worry about. So what you're going to end up with is what we call TLSs, two-level state. Those are defects the qubit can couple literally towards two. By the time you're getting closer to the defect, you can lose your energy completely and never come back. So those are the things. And then in general, the cleanness, I would say the surface dielectrics, those kind of things, we have naturally have losses. Those contribute back to the, I would say the background T1, the general T1 we're talking about. All right, good. Okay, now we have a good discussion briefly about the hardware side of the things. I want to switch gears. I want to talk more about applications. So this is important because at the end of the day, you can build something you really care about is what can you use it? What can you do with this quantum computers? So in addition to the hardware roadmap, we also have something in parallel, which really think about how to do applications. Similar to the hardware case, at the end of the day, we really care about a fault-tolerant application. This is where, whenever people talk about quantum computers, they always go to as superpower once you reach to this region. However, what you really care about, especially for experimental people like myself, like what can you do with the device in your hand literally right now? I mean, people are not patient now. We cannot wait for another 10 years to see the application. We want to see the application literally right now. So that has been the focus for the part of our team as well. In the last couple of years, we have pretty much focused on how to do these algorithms. We have done a lot of demonstrations, especially around many-body physics, with demonstrations like bound state, Majorana state, or non-abelian animals. And one of the big milestones we're hoping to achieve in the near future is so-called beyond classical applications. So what that really means. So let me spend a minute to explain what that really means. In general, when you have an application, you really want to know, hey, how good this application is. To understand that, we typically evaluate the application against two axes. The first axis is computational complexity. This is rather simple to understand. It's basically how, if I have a signal produce my quantum computer, how long it takes for the classical computer to reproduce. We fall into three categories. The first category, I would say classical easy. You can use your laptop, just run it. You can get the signal. And then the second category becomes classical challenging. It still can be done by supercomputer, for example. It just takes a little bit of time. It's not crazy. And finally, the regime you definitely hope for is what we call classical intractable. So with supercomputer, it takes too long, you're not going to do it. The other axis is what we call impact. In other words, you have to do something that has practical relevance. At least someone cares about the existence of this phenomenon. Once we have these two categories, we can actually easily see all the applications we've done so far fall into two categories. The other category very much against this axis, which is along the complexity. And this is random circuit sampling, this RCS stands for. I will cover that in a second. This kind of group of problems they are very hard for classically to compute, but somehow they're not so interesting. You don't really care about random circuit most of the time in your life. On the other hand, we also have done a lot of application related to many-body physics. We do care about this. I mean, as a physicist, many of you, our lives gradually start by training in many-body physics. The downside of that is we have smart physicists. They really can understand this easily, and we can reduce those signals with even your laptop. Okay, so what that really means is the best part, the ultimate goal for us is combine the best part of the tool, go to this region. We want to do something also capacity, in terms of computational capacity hard. And that is where we're really trying to looking for this beyond classic applications. However, in reality, this is not easy. Why this is not easy? We go back to the discussion we had earlier. The thing really stopped quantum computer from working well is noise. So let me illustrate you with a very simple three-axis thing. So when you have a quantum device, you only have three things you care about most of the time. You have system size, how large your system is. You have circuit depth, how long you can run your quantum gates. And then you have noise. In the absence of noise, in the ideal situation, you really want to go as far as possible with a large system, run as not many as possible. The quantum gate, that's how you enjoy the power of quantum computing. However, in the presence of noise can do two things. Number one, it can reduce your fidelity. The thing you are doing, the signal you get, are no longer accurate anymore. More importantly, the noise can kill long-range entanglement. Once that happens, you can break the system into multiple pieces because now your quantum correlation is local. This really has some effect. Okay, so let me show you what that means. So the first candidate we really identify. So as I said, we really worry about noise. We have to looking for carefully what are the candidate we can really seek applications. The first candidate we have been looking for is so-called random circuit sampling. I referred to RCS at the beginning. Random circuit sampling is a rather simple test. All you have to do is you have a quantum chip initialized at a certain state, and you just run a random gate signal, random set of gates. At the end of the day, you measure the outcome of your quantum computer. It's extremely simple. However, the reason we choose this is for a good reason, is because when you run random circuit like this, if you choose those circuit carefully, the quantum correlation or quantum scrambling in the language people like happen at the maximum speed. So this is really the way you can minimize the effect of noise. Meanwhile, there's an additional advantage. If you have a circuit like this, you can easily estimate the fidelity of what you have done using something called cross-entropy benchmarking, XCB, I will refer later on. And given by something extremely simple form. The first benchmarking along this direction was done by us back in 2019 with our first generation of Sigma processor. In that experiment, we're trying to do two things. We first wanted to use the experiment to benchmark how well our system is doing. Then we're trying to push for computational complexity. So what that means? What that happened is basically what we're trying to run is start with a rather shallow circuit. In other words, I just run just a few gates. I run a few gates, but I continue to increase the size of the system from something like 12 qubit all the way to 53 qubit. The data is showing on this graph here on the lower left corner. What I'm trying to show you is the XCB, like I told you earlier, basically fidelity, as functional system size. And now you can see this nice exponential decay covered by all the experimental data with all those red circles as well as those crosses. And what's more importantly, there's a black line here. This is a theoretical prediction coming from digital model. In other words, you can easily predict that by taking all the individual fidelity and multiplying them together. So this is a beautiful fidelity check because what it tells you is the quantum circuit behave or the quantum computer behaves exactly what you expect. You should expect exactly exponential decay of fidelity because your system is growing. On the other hand, once you know your system is performing well, what you can do is you go to the maximum size, in this case 53 qubit. Now you can increase the depth of circuit. You can run more and more gates with it. By the time you do that, you really push for computational complexity. This is the data I show you on right here. So I still plot the y-axis, which is XCB fidelity, but the x-axis is the number of cycles, so how many gates we're running right now. Again, you still see very nice agreement between experiment and theory if you compare the process with the black line, and it's still exponential decay. However, if you notice more carefully, on this plot, I show you those red circle, which is the data coming from the full circuit. On here, we cannot do that anymore. The system we're running right now, the circle we're running right now is beyond classical. There's no way I can compute any result based on classical calculations. So I'm missing those data. The best we can do is use those simplified circuit, those green and blue process to check how well we're doing. And we can do classical resource estimation. Our estimate at that moment, if you literally take the 2019 best supercomputer, best algorithm at that moment, it takes basically 10,000 years to reproduce the data we got with our supercomputer. So this is a very nice first demonstration. The quantum computer can just do something. You can say it's useless, but it's something that is beyond the capability of classical computing.
Can I ask a question? Can we make a distinction between, I just want to understand philosophically the distinction between a computation and a simulation. By a random circuit, you almost certainly are not doing anything that I would call a computation in the von Neumann sense. So I just, so is it just that I build a quantum circuit, so of course the output is going to be better than?
That's very legit. The way I would interpret your question is, this is computation and also useful. We do fully agree with you. Random circuit is not so useful. The way, if I want to use a language, when we call these numbers, it's a call. If literally want to reproduce the same result quantum computer is producing on the classical computer, this is the classical cost. Maybe I should use classical.
But wouldn't any quantum simulation, I'm just trying to understand why the computing part of it, because like any quantum simulation is going to produce it faster than, and I do a quantum experiment, I look at the answer, it's going to be faster than me simulating on a classical computer in these kind of regimes, right?
The answer is yes and no. If you have an ideal quantum computer, the answer is yes. In the present, no. With finite fidelity, that is no. That's why the big thing for us, beyond classical demonstration, is to really show we have very good.
I understand. Your point is that your fidelity is just
Exactly.
independent on each qubit, so you're not
Exactly.
correlated things.
So you don't have correlate error, and in fact, fidelity is good enough. Because if my fidelity goes 10 to minus 10, for example, you can just run random guesses better than what you are doing. Good. So this is a pretty exciting result because what got us more exciting is after that, we really trigger this classical versus quantum computation. Every morning we wake up, there's some classical algorithm, people tell you, oh, I built a certain algorithm that is better than yours, I can beat you. And then some other teams repeat the same experiment, they show I can do better. So it's pretty interesting competition. That to follow what you just asked earlier, that motivated us to do this again earlier this year in 2023, however, with improved processors. This is really to show the technical progress. We go to larger sizes, we build a 72 qubit, and then we end up with 70 of them. We were able to go to even deeper depths. If you remember, I show you the highest we can go is go to depth 20, and then the fidelity is almost like 0.2%. In this case, if you look at the new data, we go all the way almost like 24 to 26% cycles. With more qubit, more depth, more gate, we end up with the same fidelity, still 0.2%. What it comes down to is our gate fidelity has significantly improved. So with this improvement, and then we check the classical algorithm again. As I said, classical part really improved. We use the best supercomputer right now, Frontier. We use the best classical algorithm. We estimate to reproduce this set of data. It takes us about 50 years. I also want to highlight one more thing, which is interesting. If you look at the results just to show you earlier, I remember I tell you it took 10,000 years back in 2019. Just after just a few years, look at the experimental simulation which we can do right now, 6 seconds. So this is interesting because we literally beat ourselves with the result back in 2019, and then we beat the classical again with the result we have in Washington. So to us, it's interesting competition, but at the end of the day, as I said, it's all about improving the performance of the system. Okay, up to this point, I guess if I were in the audience, I was, look, you show us some fancy, nice demonstration. Come on, you show me one number, how you want me to get any sense of this number. I show you one fidelity. It's not interesting at all. That's really, I'm not telling you any underlying physics with the experiment we're showing. I literally give you one number. So this is actually the focus with the paper we published earlier this year. The goal is really actually it turns out you can use the same metric, XAB, to review the underlying physics of this experiment. So that brings me back to what I discussed earlier about the effect of noise. As I said, noise has one fundamental effect. When you have a noise, it can destroy the long-range entanglement and break the quantum correlations. What you can imagine intuitively is when you have no enough noise, your correlation length is high, it's long. It's longer than your length scale, you have global quantum entanglement or quantum correlation. On the other hand, if I continue to increase the level of noise, your system has short-range correlation, and then it breaks into pieces. So our goal is whether or not we can see, at some point, there's some kind of phase transition will happen. The question is whether or not you can see it. So that is our goal. So what we have done is we did a design experiment. We designed actually very nice and simple setup. We have a so-called weak link model. It's very simple. We have two 1D systems, and then connected by a rather weak link. By weak link means we have a 2-qubit gate between those two qubits, but we'll apply them very infrequently. And then you can see whether or not they can start talk to each other and grow interaction between those two, correlation between those two. The result is showing on here. It's not easy to understand what is going on, but be patient with me. So what I'll show you is still the same metric. As I said, it's XCB, the XCB fidelity. And I show you experimental data with those values dotted solid line. And then I show you the dashed line. Dashed line is a theoretical prediction based on digital error model. If you remember earlier, in the old days, they agree with each other very, very well. You can literally predict what you have done. However, if I start cutting out the noise, which is my x-axis, they start to deviate significantly. So if you're willing to dig into the theory a bit, it turns out it is actually, that's two terms showing instead of one term. In this case, in the absence of excessive noise, they start to compete with each other. This is competition give rise to this phase transition. However, it's not easy to see what is happening with standard plotting. To see things happen more visible way, all you have to do is rescale your axis. Instead of plotting XCB, what you plot is XCB ratio, the predicted from digital error model, versus dimension. The x-axis stays the same. It's a total error for your system. It's error per qubit per cycle times number of qubits. Once you plot that, you plot the curve is enjoyable because you can clearly see all the curves crossing at one single point. This finite size crossing really tell you there's a critical value of error rate below which you are in certain region we call weak noise region, above which you're in the strong noise region. If you are willing to dig into theoretic analysis, you can show this is the first order phase transition, and you can compute the correlation lenses. You can really show this is what is underlying physics. Okay, so if we have that, we have a tool to analyze where the phase transition occurs. What you can do is start to tune the parameters of the experiment. As I said, this is the weak link. What we can tune is how often we apply this link. We can apply this rather often every 8 cycles, or we apply this very infrequently with every 18 cycles. So for all those experiments, you can see this finite size crossing, which signals the existence of this phase transition. And more importantly, by the time you change the frequency you apply those weak links, the boundary or this crossing point start to move. It does make sense, but by the time you move, for example, you apply the link most infrequently, you need the least amount of noise to kill this. The phase transition pull back to the weakest level of noise. Then what you can do, so this is your large phase diagram, what you can do is take those critical points, you can construct a phase diagram. The phase diagram construct is as function of arrows and a function of how often you apply the link. Then the data, actually is basically those 3 red points. And then we compare with full numerics. This is system size that is small enough. You can compute that completely numerically, and they agree really well. And then we also develop extremely simple analytical model given by this simple equation, which is this black line. To a good extent, they agree really well. The description happened at the strong noise region, and this is not surprising because this model really did a lot of approximation in terms of noise effect. So in general, it agree really well. So once you understand 1D, what we have done is go to 2D. So in 2D, we still construct similar weak link model. We have 2 subsystems, that is 2D. Then you have a small link between those 2. Then you can still see the same phase transition as I showed you earlier in 1D. More importantly, you can see if I play the I place a gate or I run the gate sequence differently, I apply gate in a different order, the phase transition happens at different places. This is interesting to understand, basically tell you how this gate sequences really affect how the information propagate. Everything comes down to, in fact, something like quantum interferences. So with 2D understand, now you can put everything together, you can construct the phase diagram you really care about, which is 2D. So in order to do that, what we have done is run a lot of simulations for different sizes and for different gate patterns, which result I show you here. So if you look at those results, there's a few interesting features. First of all, if you remember, in 1D, the phase boundary cross a rather large range. If you look at go from 0.1 all the way to 1. However, if you look at the range of variation for certain size, this is rather tight. We're really talking about 0.1% of range. It's a very tight dependence or very low weak dependence on how often you apply the link in 2D. And also, if you compare different system size, I compare 4x4 to 4 to 6, 4x6 for different gate sequences, they are more or less on top of each other. So they also have very weak dependence on the system size, application of link frequencies. So with that, I think it's rather safe. You take all the data and you say, let me take the lowest point and take back a bit, and I can draw safely. This is the boundary between weak noise and strong noise. And then once you do that, you can place back where we stand incrementally for 70 qubit. That is where we stand. So this is the level of noise we have at 70 qubit level, and you can see this is well within the weak noise region. In other words, in this case, we can enjoy global quantum correlation within the system, and that we can ensure you can enjoy the maximized quantum computational complexity. Okay, so now I think we can put the bar a bit higher. So I have spent all my time talking about RCS, XAB. You can still say, look, this is interesting. However, still, you give me one number. What do you want me to understand from one number? So I totally agree. I think with global metric like XAB, you really understand very little about physics. If you're working in the physics lab, what you want? You want to have a magic finger. You have a finger, you can probe your system at any time, at any place. Once you have that magic finger, you say, I really understand what is going on. I want to have that magic finger. Well, if you have a quantum computer, the short answer is yes, you can do good thing to measure what we call local observables. If you can measure local observable, you can really understand what is going on. So the first example, as we're showing with our publication in 2021, is so-called auto-time autocorrelation. So what is auto-time autocorrelation? It's rather simple. It's a local probe for you to measure the correlation, in this case, between, for example, the measure qubit and the what called butterfly qubit, or where you apply the perturbations. The mathematical definition is basically, this is a commutator between the butterfly operators and the measure operator. The gate sequence is showing here is also rather simple. You have a combination of ancilla qubit and measure qubit, and you have butterfly qubit. All you have to do is evolve the system, geometry forward first. So you move it forward, then you apply the perturbation with the butterfly qubit right in the middle, and then you evolve backwards. Once you do that, you come back, then you measure. This really can directly give you a measurement between correlation between butterfly qubit and measure qubit. The nice property for using measure correlated vector like this, it has twofold. We typically call a butterfly into what that really means. If you think about, all you care about is quantum evolution, you should really not think about wave function. You should think about unitary, you should think about in Heisenberg picture. So in that picture, what we care about is operators. For operators, we have two effects. First, operator can spread in real space. In other words, if I apply some operation here on certain qubit as function time, the effect can grow. Go to nearby qubit and grow gradually. On the other hand, if you go to operator space, it can also grow. I can describe this with one operator, with more, and more importantly, those operators can start entangling each other. So this is what we call operator entanglement. It turns out operator spreading in most cases, especially for random circuit, they're classically easy to compute. you can use things like population dynamics to really predict very precisely what is going on. However, the computational resource coming from here, whenever you have operator entanglement, this is hard. Things goes exponentially hard in this case. What is nice about OTOC is, depending on how you measure this, if you measure average OTOC over many different instances, you can directly measure operator spread. If you measure the fluctuation between different instances, you can measure operator entanglement. So let me show you the result, whether or not this is the case. So the first thing we actually try to see is operator spreading, how the information is spreading across the system. You can literally visualize it with your eye. So what I show you is a color plot, show you basically the correlation between the measure qubit, which is black here, to the rest of the system. When they're in yellow means basically there's no correlation between the measure qubit and that particular qubit. Whereas in a different color like blue or greenish, that means correlation is established. Then you measure that as function of number of cycles, how many gate you apply to that. Then you can see the information really spread. You start from local, you go spread to your neighbor, next nearest neighbor, and so on, spread. When you got to 15 cycles, in this case, you can see the correlation really spread across the entire system. This is where you can show now you have entire correlation. You can literally see that. There's no reason to argue. You can see that we have entire correlation, and this is where you can really thinking about whether or not you can enjoy a little bit computational complexity. On the other hand, operator entanglement is harder to resolve because oftentimes operator entanglement and operator spreading, they bound with each other. There's no way you can do one without the other. We have to really design the circuit very carefully. So what do we have end up with is we design the circuit, we start with only the Clifford gate, then we gradually adding non-Clifford gate. The nice thing for Clifford gate is it only triggers operator spreading. In other words, if I have an operator, I can start locally here, we convert it into another operator string, and then they just spreading in space. However, by the time I add non-Clifford gate, I need more and more operator strings to describe what's happening in the system. So the result is showing you here in a second. It's just a lot of data to load. Okay, good. The result is showing you here. So it's a little bit messy and have a look. Let me walk you through. So whenever you start, so what do I show you here is auto value we measure as function of different instances along the y-axis, and the x-axis is how many non-Clifford gate we add. Go to the limit, add 0 non-Clifford gate, the number just jump back and forth between 1 and -1. As I said, this is because you just convert from one operator string to another one. There's nothing fancy about that. As soon as you add non-Clifford gate in, add entanglement between those, they start taking values between 1 and -1. Now you can see that when you apply more and more, there's more values between 1 and -1. So now what you can do is really analyze those data, as I said, by analyzing average OTOP and OTOP fluctuations. If you go to average OTOP, which I show you here, you can see this will remain almost at constant. Basically, in this case, by the time I'm adding non-Clifford, I can retain operator spreading at the same level. However, if I look at the OTOP fluctuation, which is literally compute RMS of those curves, you see exponential decay of the signal. That really tells you the entanglement of operators is really growing. This is signature of it. So with that basically understood, what you can do is go back to compute how hard this is to reproduce the same signal classically. So we have compute the classical time. In this case, it's not so hard to compute. In other words, the y-axis is the time for single CPU to produce the same signal. And the x-axis is the number of entangling gate we apply to this. So the data we have shown you earlier barely cost something like an hour. So it's not that hard to compute. However, if you can manage to improve the performance into the regime, say you have 400 or 500 number of entangling gate, this is where things become very hard for class computer to compute. Another challenge I do want to highlight, if you look at those 3 data points here, which I zoom in with the actual data I show you on the right, just look at the x scale in those 3 points. I start from 1 and -1, I show you earlier. And in order to resolve the data, by the time I add more and more gates, I go to 0.1 and minus 0.1 and 0.1. What basically is really telling you is that by the time we add more and more entanglement gate, yes, the computation complexity grows exponentially. Unfortunately, the signal we're trying to looking for also gets suppressed exponentially. So this is a real challenge. When you try to measure local observable like this, just as you wish for physics experiment, you have this computation.
Is it because the control is so hard on the swap grid, on these non-Clifford grades? Why? Is it because of how you have to address them, that you have to address many of these things, or why do you see this?
Let me go to the next slide. You asked the right question. It's a combination of all of them. So what you described is the fidelity or whatever performance coming into play. That will, you have a raw signal. The final signal you will be observing is raw signal times fidelity. This is how we're talking about. On the other hand, even in the absence of noise, you have perfect fidelity. This signal can get exponential support because your Hilbert space, the effective Hilbert space, gets growing. So the way to look at this, thanks for the question, because this takes me to this slide. If you have a look at observables, I show you this light cone effect, as the things gradually, your information gradually grows. The same thing apply for what we call effective quantum volume. This is the volume things matters. In other words, if I have a look at observable at a certain time, a certain space, not all the gate matters, not the gate, all the gate at all time matters. It has this same light cone you should care about, only the thing within this light cone matters. So in this case, let me take you to the next slide. If you really care about what you're measuring, the fidelity of the signal you measure has to be cared about within this light cone. That's the answer to your question. Number two, when you talk about computational cost, don't call the entire, oh, I have this size of system, this number gate, it doesn't matter. Only the thing within this volume, especially that's the effective area. If you read the paper and make the link probably on the previous slide, that's the effective area that matters. The fidelity got exponential support over the volume, and then the cost goes exponential growth with area. At this moment, this becomes really a difficult problem by itself because in order to see the classical, beyond classical signals, you really carefully need to choose the trade-off between those two exponentials. At this moment, you really talk about prefactor analysis. It's not just about the function itself, it's a prefactors. But to us, we still feel this is an exciting moment because if you allow me to come back to the original diagram I showed earlier, this is what you want to get.
Can I ask a question about that?
Yeah, please.
So as I approach the Lee-Robbins bound as fast as you can go, you get better or worse in the quantum? I'm trying to, are you going to be better for faster scrambling, or is the advantage grow with faster scrambling, or slower scrambling, or it's hard to, from this argument, it's hard to figure out.
Yes. You look at my face. It's, the face I'm having now, this is a very hard question because it's a computation too. In order to minimize the effect of noise, I want to scramble as fast as possible.
Yeah, exactly.
But if I scramble too fast, I go
Yeah.
to large volume, my signal can
Yeah, that's why I was asking what the trade-off between these.
The trade-off, as I said, is all about the specific signal you're looking for down to those prefactors.
I see.
It's all about those prefactors. And then they vary from application to application. There's also no free lunch. So I show you two examples. This is the goal, which the region we're trying to go to. I show you two examples. One is RCS. They're difficult, they're not so interesting. Or I show you the example with OTOP. They're interesting, they have physics. They're not that hard, I just want to reproduce. So we're not there yet. Well, at least a step away. Either you figure out how to understand physics a bit better, or you really figure out how to increase the capacity of your signal such that you can to this region. But that is exciting moment because this, at the moment, there's most likely how to do that trade-off will require a supercomputer itself. You cannot answer the question by your hand. With that, I'd like to close my talk with
Can I
one
ask a
last.
question about that
Yes,
also?
please.
As you get these bigger and bigger, I'm just wondering, is the noise become correlated across the qubits because it comes from the control systems as opposed to independent thing? And that would completely even kill these scalings, right? Yeah.
Not entirely. So the biggest, if I do a budget in terms of the, I code fidelity, I have a case fidelity. The budget typically are 50% coming from what we call coherence.
Okay.
Coherence typically ties into material itself. 30% coming from known like coherent error, which is contrary refers to. The another 20% is God knows what it is. Yeah. So let me close my talk with one last thing, which is a little bit advertisement. Again, I really want to thank you for the wonderful team. You're fantastic to work with. I do want to advertise to all of you. We have many ways to engage with academics. We give out research grants, we sponsor research, we have visiting scholars, we host students, we host intern, we provide fellowship to PhD students. If you really found any other thing we're doing interesting, seriously, come talk to us. We are just like a mile away from here. Okay, with that, that's my talk. Thank you for your attention.
And we have time for questions. So can I invite questions from the audience?
I had a question, sorry. I had a question. I was just wondering about, obviously this is all in a superconducting circuit. And I don't imagine it has any impact, but would you, disorder's an issue or cleanliness is an issue with your superconducting circuits. Do you get any advantage once you're below TC? Is there any advantage gained by just going lower in temperature? Does that affect behavior of the gates?
Yes. So the temperature comes into two effects. Number one is, as I said, just go below TC. That's how you reduce the dissipation of this. Another one is noise. It's a thermal noise. If you think about the frequency we typically work with is, say, 7 gigahertz. If you translate that to temperature, it's just hundreds of millikelvin. You have to go well below that temperature, such as your noise is not allowed to induce any, for example, excitation of your system. So minimize noise is a big thing.
Do you use something like a dilution fridge then? Or?
Yes, we use dilution fridge. We work at around 10 millikelvin. And we do filtering as well.
Other questions? What about the potential for materials improvement? You're working with aluminum because it can be scaled up beautifully, I guess. But you mentioned, I think you mentioned tantalum. And what would be a dream material for your operational improvement? What would make it worthwhile to abandon aluminum and go to a new material, which would be a major step, of course, to do that? What would it have to do?
Yes, so material affect us in a couple of ways. I don't know that it's all about coherence, but coherence are affected in different ways. So it first affects us overall performance in terms of coherence time. In that case, those losses typically not coming from metal itself, they're coming from interfaces. For example, I have substrate, I have metal. Between those, I have at least two interfaces. I have substrate, metal. Metal always clean. Any contamination on this interface will flow back to the loss. You have metal. Metal has interface between metal and air. You have contamination, you have oxide. Those will cause losses. So on that layer, my dream will be extremely clean interfaces, and you don't have oxide. If you don't have oxide, that saves our life much, much more. That's number one. Number two, I love to have perfect material, have any kind of defect, especially on junction. If you look at, let me go back to this. It's kind of pretty amazing. We build those qubits with hundreds of microseconds. Look at how crappy this structure looks like. It's crazy, a lot of grains, rough edges. Look at those dark area that contaminate from the fab. If you can really clean this up, I think you can increase your coherence time, and you don't see those defects in your spectrum. So our word is, I was wish to show you a picture. This is beautifully clean, smooth edges, everything shiny. No, we're far away from it.
Thank you.
Yeah.
Okay.
So you said you use aluminium for your superconductor. And I was wondering, you said, I think, if I heard you right, you said that you avoid oxides. And for example, something like a copper oxide, maybe like a coupe would not be good for an application. Do you guys exclusively look at BCS-like superconductors, or are you looking at unconventionals?
Yeah, we mostly stay at low temperature, I would say the conventional superconductors, because if the high TC, yes, you can imagine high TC has a benefit. I don't need liquid dilution fridges. But ITC has very short coherence lengths. If you look at our circuit, they're millimeters. I don't think you can preserve the long-range coherence over this range. So you kind of have to stay with it. The reason we choose aluminum is just for practical reasons. First of all, it's one of the most well-studied superconductor. Number two, junction, aluminum junction so far is the most reliable, only the best known junction we can build. Aluminum oxide, so far, is the best oxide we can ever work with. We tried many different oxides, it never worked. Aluminum oxide is only one of them.
Amazing. Other questions?
What is that? What is entangled operators?
Oh, you're talking about operating entanglement?
Yeah, what does that mean?
Yeah, so if you think about unitary, let me use this as an example. I can describe with the system I have local, say, bit flow at certain place. Or I can describe, still I just have 2 bit flip to nearby cube. To me, this is one single operator string. It's just I grow in terms of space. However, if I start adding something like, in this case, non-Clifford, you need to multiple operators. I need to do this bit flip. I need to do that, and they need to happen. Those things have superposition of each other. You have to use all of them to describe the unitary process will happen. Those operator string is start entangle with each other. Just like if you can translate that to qubit, it's just like qubit entangle each other, operator can entangle by themselves.
Okay. Yeah, that makes sense. Thank you.
All right.
Can I follow up on that? What's the longest entanglement length you've achieved in your computers so far?
Well, if I believe what I showed you earlier, I think this is 2 years old data. This basically means we can achieve the full range interaction, in this case 53 qubit. The latest experiment we have done more recently, I think we extend this to something like 70 something qubit.
And how far apart would those qubits be physically?
If you count from this one to this one, I think this is on the order of like 10 qubit.
How about?
10 qubit on the order. If you count the distance from say this end to that end, the linear distance is on the order of 10 qubits. You can also ask what is limiting us to go further. My suspicion is defacing. You lose your phase very quickly.
But physically on your circuit board, how far apart would they be?
Oh, you're worried about the physical length.
Yes.
Every this kind of thing typically is on order of a few millimeters, so times 10 is on order of a couple. Our chip side typically is on order of just a few centimeters. You can go from one end of the chip to the other end of the chip.
Well, we've got a tiny bit more time, so I don't want to.
You can put this on Google Bus.
Could you just tell? Oh, go ahead. Yeah. Do you have a question?
No.
Could you just describe a little bit more carefully what fidelity is? You had this logarithmic plot of fidelity decaying exponentially
Yes.
with a number of cycles. Can you give us a more precise definition of your fidelity?
Yes. Unfortunately, I don't have a backup side to quote you exact numbers, but I can tell you roughly numbers.
What's your experimentalist understanding of
Yeah.
fidelity?
So the fidelity in this case, as I said, the black curve, how you produce that curve, it's a multiplication of single qubit fidelity,
Yes.
2 qubit fidelity, and without fidelity. At that moment, our single qubit fidelity is like 1 10 to minus error, not fidelity. You can do 1 minus of that. It's 1 10 to minus 3. Our 2 qubit error in that case is 0.5%, 5 10 to minus 3.
Does that mean that the error rate would be, when you say the fidelity is 10 to the minus 1, for example, does that mean that 10% of the time you're getting the wrong answer?
If it's 0.1%, that means if I run this 1,000 times,
Yes.
there's a chance one of the case, and this is wrong.
Okay,
That's how we call the fidelity.
okay.
And then the last fidelity is without fidelity. At that moment, we end up with something like 2%. Then we improve quite a bit. And here, in this case, I think our single qubit fidelity got reduced by something like, no, not fidelity, error got reduced something like 40%. But our 2 qubit gate got improved almost by factor 2. So that is a big room.
Okay.
I was just wondering what, is it well understood the sources of incoherence in these materials? Because in the unconventional superconductors, it's a bit of an open question. But in BCS, what are the factors that influence it? Obviously, you have disorder, in temperature, but is there anything else?
So the incoherence, as you mentioned earlier, it's a budget. There's a couple of places. We don't have perfect material. They have oxide on the surface. Those oxides are lost. It's just like any dielectric, they have certain loss. So you can take that and you can convert that. I don't know if you go to like electrical circuit analysis, typically people talk about Q factor, quantity factor. You can compute the same thing. The effect is acting as a resistor in the circuit. I have L and C, they are superconductor lossless. Dielectric loss like this, you shunt it with a resistor. So you literally can compute the T1 loss from that. That's number one. We have vortex, naturally. We have flowing of superconductors. When you have any weak field, you can vortex start moving, the cost dissipation.
Superfluid, right?
Yes, the cost dissipation. That's the second one. And we have quasi-particles. Quasi-particles move around. We can grab energy from qubit and then tunnel across the junction. And as I said, what we have is superconducting circuit. I have LRC. You want to control it. Want to control it, you need to attach control wires to it. By the time you control wires, your control electronics, towards the end, that's a 50 ohm. So how strong you couple with this? You need to be strong enough such I can control a qubit, but if it's too strong, it really destroy it too. So that's many resources. To good extent, there's still a lot of them.
Because ideally you want, obviously you want the longest coherence length.
Absolutely.
Is there any research currently that you know of that's in BCS like superconductors that's trying to understand how we could increase that coherence length? Or is that something that's just not changing? We can't really change that very much.
My gut feeling is in this case the physics of superconductor is less relevant. It's mostly true like raw material. Can we get rid of oxide? If the reason we go to tantalum is much harder than oxide. And once you have oxide, that represents something like dielectric, that introduces loss. The superconductor probably won't come into play because sometimes people design special junctions. They design pi junctions, for example, that can have certain shift and minimize defacing. But in most cases, superconductivity is not the metric we truly care about.
Yeah, because the tantalum thing is kind of intriguing, right? It's just like happenstance that, because when you say tantalum is something that doesn't form an oxide, it doesn't seem, it seems like the bar is pretty low because tantalum does like to oxidize.
Yes, this is an interesting journey the whole community went through because we use aluminum for the community for 30 years or something. There are definitely people try different material. So for example, niobium, that was not successful because niobium has very complex oxide surface.
Yeah, niobium I would not suggest, right?
Yes, people try, it doesn't work. We try other material. Back in the time with back in USSB, we tried titanium nitride.
Yeah, I was supposed to say, what about nitrites, right?
It's beautiful.
Okay.
We have very nice results. The challenge, what's the challenge there? It's a compound. It's very hard to produce the same result. Yes.
Oh, because the nitridation varies.
This concentration can
Yeah.
vary dramatically. And this is just a technical challenge.
Yeah.
You can literally see the color changes by the time you fab the wafer.
Yeah.
So it's very hard to follow control. So you're really looking for a single element. So the interesting story goes to the first experiment with tantalum happens in Princeton. It's a person from superconducting side that go talk to a materials scientist. Oh, let's just brainstorm. I don't want oxide. Like I say, let me look back to my book. They come back a little later and say, let's try tantalum. And it was big success. They literally have one hypothesis, is how can we get this? I don't think we can ever get it with oxide, but I think the hypothesis that the oxide faces for tantalum probably is simplest. And it probably has also very thin layer oxide, which really helps in this case. However, it doesn't mean this is a trivial story to finish. Unfortunately, tantalum have different phases. There are alpha phase and beta phase. If you go to the wrong phase, they're horrible. You have to grow nicely to go to right phase. So it takes them quite a bit to figure out the right growth condition.
Thank you very much.
I was just wondering, has it been investigated if you could use, increased pressure to, because I know that can increase your TC in, let's say, the cuprates or even BCS-like materials. But does that affect your coherence length? I imagine it would increase it. For example, could you imagine an angle cell that
Those technical change.
So,
I understand where you're coming from, but high pressure and low temperature, they're not compatible with each other. You cannot dump tons of gas into millikelvin, they will freeze. So I don't think that
Yes,
that
not
is just
convert- yeah,
technically challenging
okay.
for us.
Let's thank our speaker, and we're going to take a half-hour coffee break. Percy wants to catch us for a picture before we all go away and have coffee, so don't go anywhere. We're going to go outside and group for a picture out there.
Models have now demonstrated some form of scaling and emergence. GPT-4 is 1 trillion parameters, so think of a variational wave function with 1 trillion parameters. And I don't know how many tokens were pushed through it. I should know that number. But the scale is comparable to this, and because that many floating point numbers have gone through it, it costs $100 million to train. So this ties to the point that only industry can afford $100 million to train these things. But if we had $100 million, we could have a great variational wave function. So that's my pitch. I'm gonna fly through a bunch of applications now, and just stop me if you see anything you like in the next 5 minutes, or we can discuss things after. So this is what we're doing with these language models. Okay? First off, if you have a time sequence, if you have data that's a time sequence, like qubit data, and I kind of showed the 1 and 0 example, but you could have all sorts of real numbers. These things are great at prediction. So I mentioned, using AI in the control stack for quantum computers. This is already a reality. Here is a control algorithm that we wrote for a trapped ion quantum computer at Waterloo, run by Rajul Islam and Crystal Senko. Here's a Rabi flop, of a single ytterbium ion in the trap. We have some training time, and then we have some prediction time, and it's only 1 qubit, so I can fully, figure out the exact time evolution, and you can see that you get perfect correspondence. So what you've done here is you've unrolled, in this case, an R and an N. Each one of these blue dots is 1 recurrent cell along the time sequence, and you can just imagine, if you can do this type of prediction in silico, you speed up your clock speed of your quantum computer gets faster because whatever you need to know out here at long times can be predicted by short time behavior. That's a real simple example, I think, and we routinely use language models for this type of control. Here's another example, variational ground state. So I mentioned you can train these things variationally. Rajiv and I had a discussion yesterday about whether this beats state-of-the-art methods like tensor networks. And the answer is yes. These variational wave functions, if trained off of an interacting, strongly correlated Hamiltonian, like here's an L by L triangular lattice Heisenberg model, which has a famous sign problem. There's no sign problem in the variational formulation of VMC. Here's RNNs, so here's the language model minus the DMRG energy. So the DMRG wins until I get to 12 by 12, and then I get the lowest energy from the language model. So I don't know what the correlation function, but there's no surprises in this model. You know what the ground state is. It's got some symmetry breaking state. But just to point out that these things make great variational wave functions, and they're relatively efficient. Out here on the large, L by L sizes, they're only using 0.1% of the number of parameters of the DMRG. And I forget the actual total number. But again, the hope is that if we scale these things, they will.
Sorry, what do you mean by the parameters of DMRG here?
The bond dimension is, you increase the bond dimension, and that's how you increase the number of parameters. So the tensor network is really another autoregressive model. It's just another way of parameterizing a wave function.
Can I ask a question? Have you tried to estimate things like entanglement by using mutual information between your softmaxes and seeing how well it does?
Between our what?
Well, you have whatever between your conditional probabilities, right?
Mutual information between different parts of the system.
Does that correlate well with entanglement in your variational analysis?
Are you talking about like if I divide the system into region A and B? And, yeah, I mean, that's
So I'm just wondering how well it estimates things like entanglement.
great. I mean, it's a function of training, but we routinely use, okay, let me show you another example. Here's from the other program. So, I get a lot of data from Misha Lukin's group who builds, this is basically a transfer field Ising model. So there's no sign problem. So I have quantum Monte Carlo that works for this. But we get a lot of data from his experiment, and his data looks like this. It's just projective measurements, zeros and ones of the qubit states, essentially. So there's a special, because there's no sign structure in this Hamiltonian, if I learn a language model from this data, it's the full representation of the wave function. And then I can do any trick I want in terms of measuring things in different bases. So here's not directly your question, but again, assuming that this is the form of the wave function, I can do things, now that I have a parameterized, so I called this theta before, but I have a parameterized version of this wave function. I can do tricks that we do from variational Monte Carlo, for example, the local estimator, which basically just lets me measure off-diagonal estimators or expectation
Yeah,
values.
so you can, I was just asking because with energy-based models, you can do this stuff too, but
You
with
can, it's the
recurrent
same.
neural networks, what you can calculate is entanglement, which I don't see how you can do from energy-based models very easily, or maybe you can.
Second Renyi entropies, second, third, fourth Renyi entropies. So I don't have the estimator here, but there's a way to do it with the nth moment of trace rho to the n.
I get it.
So I was gonna, in a more physicsy talk, I would show that. So we actually give entanglement entropies back to, say, Misha when he gives us his data. And so it's incredibly useful. They say, the experimentalists say it's useful. One more example. So this is actually an old work from 2019 when we were using an energy-based model, because actually here the partition function is canceled out. But now these things scale much better with language models. And so just to go back to Rydberg, atoms and GPTs and transformers, this is the new architecture that we're basically building for the experimentalists. And it has the typical structure of a prompt that goes into an encoder. And I just use a prompt that's a Hamiltonian. You just take your Hamiltonian, you have a certain number of parameters in there. I prompt my model, and then for every prompt I train it with, here's my autoregressive path through a two-dimensional atomic system, which is basically one projective measurement. Once the thing's trained, I can literally just prompt that model and vary the parameters of the Hamiltonian. Here's an example for my students that shows how it works. Here's just the energy of a 200, what size is this? I think it's a 16 by 16, so 256 atom quantum device. It's been trained on the arrows, so there's some phase transition we were looking at here and so on. I have the exact answer for the energy from my quantum Monte Carlo, but the blue is the result of the GPT model once prompted with different Hamiltonian parameters. So you can see it's basically perfect along this line. And what it tells you is that, again, it's about AI lowering the cost of prediction. I can predict what's going to happen in my experimental system. I can, this can be experimental data that I train on, and I can use this thing to predict what would happen in regions where I haven't tuned the experiment yet. So I think these architectures, these language models are super flexible and allow for all sorts of integration back and forth with experiment. Error correction is another one. Google uses this for error correction, right? But anyway, so it's all these things are, I'd say, being implemented in as we speak. And so I'll talk about my discussion points, but maybe a question before that. So language models are here. We're training them all the time. They can be trained variationally, and they can be trained with data or any combination thereof, which I think is super interesting. You can ask about digital twins. You think about quantum advantage. Google builds a machine that can't be simulated, but if you have data from that machine, is it possible to learn the state of the computer in one of these language models with data? Why not? We still don't really know how that scales, how the learning problem scales when you use the data-driven cost function. So they're powerful simulation tools, I argue, and they're only getting better and better every year that we work on them. What's still hard about it? It's the optimization. When we have that loss function, we have all that data, where's the sign problem go? Where's the hard problem, it's somehow in that optimization. So what language models are is very good, heuristic tools for optimization, and so those heuristics seem to serve us very well, I would say. But they're still based on gradient descent. And just to get back to that point about emergence, we know that these language models scale. We know that they have emergent properties, and those are also the goals of quantum simulation, either numerically in silico, or if we build a quantum computer, we want to see emergent phenomena when we get enough qubits together or when we get a big enough simulation structure. So I think it's really interesting now because what we're actively doing, and again, this is happening in real time, is we're taking quantum data, we're learning language models, and then we're doing things like this, which is predicting, the outcome of the quantum, or the output of the quantum computer in different regions. And you can either interpolate within distribution, or you can interpolate out of distribution, which is like this stuff here. And so both of these things are going, both these paths, in distribution and out of distribution, are being used, both in design and so on, but also in active feedback with the quantum computer. So it kind of begs this question, like if we don't know what the AI is doing, do we really have full control of the quantum computer? And if we observe emergent phenomenon in a device that was built with an emergent, complex AI system, again, have we really achieved anything? Those are my philosophical points. Thank you for listening.
Thank you. We had several questions during the talk, if there is room for one more. We're running.
Yeah, so you mentioned that you can code the phase and you have no minus sign problems in your encoding. But if I run that back against you, does that mean that I can completely reformulate quantum mechanics in terms of probabilities
Yes,
and amplitudes altogether?
I think so. Why not? Yeah. So, I mean, you can encode all the entanglement. So one of the generative models we have is a POVM version. So you have measurements along different bases or different axes, and then that's fine, kind of all the phase is encoded there, and all the entanglement is encoded in the classical generative model. I think there's nothing stopping.
I think Bohm would be very delighted to hear your answer.
Very practical. Thank you.
Okay, thank you. Thanks again. Okay, our last speaker today,
Something missing. Yeah.
Like a bell inequality?